Okay, so let's start with this. I I am building a circuit. It's a very simple one, and this is the book that it comes from. I would actually really would recommend this one if you're like trying to learn electronic stuff, because it covers the very basics. It's really meant for like kids and teenagers. Um, the cool thing about it though is that it has some very simple projects and it's very cheap. It's really like $50, I think it was. And for $50, it is actually very cool. Like you get a lot of stuff. Um, I pretty much skipped all of the before. I read the book almost entirely, but I did skip like almost all of the first projects because I don't really care about those that much. Really, the reason I bought it. So maybe I should talk about that. The book, it's an Arduino Uno. Um, but this is like so instead of just getting the board, which is really what I wanted, it's more like a kit with like a starter thing, and it gives you like a couple of things to do. It comes like with an instruction guide slash book, project book, and right now I am doing chapter 10 or project 10, which is like a small motor that you use. And where's the motor? I don't know where it is. I think I left it somewhere here though. Ah, cabrón. ¿Dónde lo dejé? Oh, it's right here. So this is the small motor that is gonna power. So as you can see, I'm like halfway there. I'm almost done. And I wanted to record it because there's not much guides and stuff like that about this kind of stuff. So since I'm learning it all on my own, I kind of want to make it a little bit easier for everyone else to learn too. So one reason why I'm trying to learn this stuff is because I'm trying to make an electric car. But the electric car is not just like the whole part of it. Really, I want to learn about electronics, and one of the things that I want to learn about electronics very well is designing inverters and using AC to DC power conversion without with switching with transistors, and I want to build that kind of stuff. And for that, that's why I got the board, because the board actually has a little bit of capabilities of doing switching stuff. um, but that's very far ahead. Right now I'm not doing that. Right now, as you can see, I'm just doing the small motor. But let's continue. Right now, um, I'm like halfway done. So for example, here I need to connect the motor. The motor goes here. And here. Connected the power. connected the comms, the ground, the power here. So I'm missing 3 comms on the top, right? The transistors. So I'm missing 3 comm wires. You could think of it maybe as this is not a full review of the product, but yeah, it's pretty cool. I would recommend it. It's not bad at all. Maybe it's a little bit kind of basic on the stuff that it covers, but again, for $50, I mean, realistically, you're buying the chip, right? But it comes with a pretty cool tutorial. You can think of it that way. Like it's for free. It's like a tutorial box that comes with the chip. And for $50, it's really not that bad. And by the way, I had never ever done this before. Well, this is the first time that I kind of like learned about small circuits making. Mainly I deal with like bigger stuff, but yeah, with like small stuff like this, I've never ever dealt with before, and my fucking hands are too big. I'm always fucking struggling trying to put this in. So that's the 2 comms, and I need the 3rd one that goes to that one, and I connected it on this side. There is a chance that this won't work, but let's see. So this is all connected now, as is instructed on the book. Now, the second thing that I'm going to show you is that it doesn't actually connect it to a battery. No, here's it. It connects it to a battery, but I'm going to connect it to this stuff. This is an adjustable power supply, pretty much. I got it because, again, this is not the only thing that I'm doing. I'm doing some other stuff too. So it was gonna be pretty useful to just not rely on batteries or a single power supply that I have to get a specific transistors and resistors for it, because I don't want to do that. It's just better to have a little bit of variability on the power supply that I have. So I am going to be using an actual power supply, not a battery. But I'm done. This is all connected. Now, once the thing is connected, you have to upload the code. There's a code. So I'm going to upload the code. So how you do it is this. You grab the thing, it comes with a wire. It's a USB 2, I think it's called. And you connect it. You download the IDE, and you upload a code. Either you can write it down. I already saw the thing, and when you download the Arduino IDE to like upload code to the stuff, it already comes with prepackaged templates, and it includes all the projects that come on the book. So you don't need to write anything, you can just upload all of the stuff. So I'm gonna go do that and then come back, and I am gonna wire it. Let's continue. So I uploaded the info, right? Now I only really have left to connect the communication pins to the board. Well, no, not really. Not quite done. I do need to connect the power. So yeah, I'm not exactly done here. Let's continue. So this one goes to... Oh, by the way, I learned something interesting. You have to be... I didn't notice this before, but integrated circuits like this one. So this is an integrated circuit, right? I don't know if you can see it very well. Or I can show you this one. Like that one. This. So they number the pins, right? It's pin 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10, whatever how many pins it has. But they're so small that they're not numbered, really. They just go left to right, top to bottom. But they're not numbered. You just have to know the number. Now, actually, I didn't notice that, you can put it backwards. You can connect it backwards, and it's, I guess, a problem because I'm not guessing they're symmetrical on both sides. They have a notch, a little notch. So if this is the circuit thing, there's a little notch here and more of a bump down. Like you can differentiate which way goes up and down. And I saw it. You can see it on this one too. If you see on this integrated circuit right here, it has a little notch here on the top that it doesn't have on the bottom. So you have to be attentive to which way you put it. It doesn't really tell you or show you. You just kind of have to be careful, I guess. But that's the only thing. Everything else, yeah, your hand's gonna be your most limiting factor. So that goes there. This goes here. So this goes to 0. And 4 and 5. So this goes to 4. This goes to 4. And this one goes to 5. Mm-hmm. 5-volt and ground. So that one is talking about this one. Ground, 5-volt. Uno, dos, tres, cuatro, cinco. 1, 2, 3, 4, 5. 1 com, 2 power, connected to power. Everything seems to be connected. Okay, it works. Power, this goes to power. This is connected to the motor, the resistors, and then the battery. So this is a connector to the battery. Huh. Now that's a problem, isn't it? Because How do you know? Fuck. Oh, I can see it. Thank you, Jesus God. So here's the problem, right? I don't want to use a battery because it specifies on the book to use a 9 volt, the big square batteries. I don't have one, and I really didn't want to get one. So, but the connectors from the power supply, obviously they're not pin connectors, they're clamps that open and close. So you cannot hook those here. So I wanted to connect the clamps to the, now where did it go? To this one of the battery. The problem is that I didn't know which was negative and positive. Thankfully though, I can see the wires sort of. So I think it goes like this. Now let's hope this works. If this doesn't work, really, I don't really care that much. Actually, you know, talking about that, the good is the book is pretty good. You know, everything was fine. It was very pretty. The main thing, though, I think, is the chip and the book. All the components, and I'll show you. These are the components that they give you. Obviously, I open everything up and everything's used now, but comes in like Ziplocs like this. You can clearly tell that they got like the cheapest stuff available, which makes sense, right? $50 is not that much. But my previous project, which is chapter 9, I think, didn't actually work because this, you have to use this one, and the female connector, it doesn't work. When you try to connect the pin to the thing, it doesn't really go sufficiently in to be able to be connected to the board. So I couldn't actually finish chapter 9 because of this problem. Again, I didn't care that much. You know, I'm not gonna go around trying to solder cables and stuff like that. So I just moved on. But it is a problem. You know, one of the negatives about this one, like the components that they give you are kind of like the very basic cheap stuff. For example, here, I can tell you right now I have a problem. This, I think they call it a potentiostat. It's just a knob, really, to control like the speed of the motor. It's very cheap, and you cannot really connect it very well to the board. So it might as well even not work. But again, I'm not gonna like care too much about it. Really, I just want to see the thing work. And you know, it's Christmas. It's a small project. I'm not gonna go crazy about it. So I don't really have a huge problem. But if you do get the thing, you know, don't expect it to be like super high quality stuff. Really, they're just giving you stuff to try out. If you want to. If you don't want to, well then you probably got the thing for the cheap. For the chip, the Arduino Uno. Either way, the rest is just bonus stuff. So yeah, now I have finished connecting everything. Da 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 da. This is the code. Attach the battery to the connector. When you press on-off switch, the motor will start spinning. If you turn it into chamber, it will speed up and slow down. Pressing on-off button another time will stop and more. Press to the speed. Also, if you knob on the pod, you should see more speed up or slow down depending on the value it is setting. Okay, so I think it should work now. It says connect to the computer. I had to bring my computer because you need to power with a USB cable. So I connected that one, right? Computer is on. Now I'm gonna turn this on, and with this one I have to be careful because this can supply way more than this can handle. Five volts, it says right there. I don't know if you can see. 5 volts. So, should work. You know what? I'm actually gonna do 4 volts because I don't want this thing sparking on my face. Most of you that know me should know that I cannot really see very well, so I have to get my face really close to everything, which kind of sucks when you're doing this because I had already had one problem where it freaking sparked on my face and I don't want to repeat that. So that should be on. It's not working. Oh, it's working. It is working. Whoa. Oh, it's... So this is a magnetic... I think these are called... So it is working actually. I don't know how can I show you that it's working. Maybe you can hear it? Or I can get my phone closer. So, let's get my phone closer. Let's see. So this is a motor, right? Now when you turn this knob, where's the camera? I can't fucking see anything. And it spins. Now, one cool thing that I wanted to try out, right, is what's the limit of the... So, one important thing that I'm learning about, the reason why I'm learning about integrated circuits, right, because of the transistor thing, is because you can control a wave and a current to like power motors. And not just motors, but for example, electric stoves too. And energy recovery and charging of batteries, everything is done with integrated circuits. You don't just connect the electrical outlet to like a battery and magically charges. Really, you have to transform the electricity to a different form in order to use it. This is one example. You're transforming it from one voltage to a different one, and it limits the amperage too. So for example, this is what I wanted to try out. If I lower it, let's say to 2.3 volts, right? And if I put the motor to the max, it actually doesn't work. So there's a limit on that integrated circuit to a lower end voltage in which the thing just doesn't work. And for example, right now at 4 volts, it does work. And I can control the speed actually from here. Now, there should be an upper limit to how much you can do it because I can actually pass 5 volts and it spins faster. And I don't want to continue anymore because I don't want to burn my face. But yeah, so it works. It's very interesting. So knob, potentiometer, and well, let me increase it to 5 volts because it struggles to move. And So that controls in which direction it spins. And this turns it on and off. So yeah, how this thing works, I'm gonna explain it. This board, can you guys see this? And actually I shouldn't even do this. I shouldn't leave these on the floor because it's metal. So let me put this book underneath like that. So I'm gonna explain now how this works exactly. So an electric motor, the way that it works is you have to send a current through a shaft, and the current is gonna make a magnetic field. So this is the shaft, right? It turns. And around it, there's gonna be a couple of coils, copper, or not copper necessarily, but like a winding cable around it. Now the shaft usually is gonna have like some sort of indentation on it, or a magnet or magnets on a certain position, so that if you send current through one side, it is gonna try to spin that magnet to that coil. And then what you do is you spin where that magnetic field is so that the shaft follows it. That's the very basic of like a electric motor. If you do it the other way around, now the thing is off, so it shouldn't really change any values or anything, but a generator or an alternator works the exact same way, but it's the other way around. You force spin the shaft to get a value to get a certain voltage or a current trying to flow through the coils on the outside. Now, why do you need to hook up this to the board? It wouldn't work if this was not connected to the board. Well, here's the reason why. The thing that controls where the magnetic field is around the shaft, it's the circuit board. You really need a computer or at least a very basic circuit to like try to move an electric motor, because most motors today, electric motors, use it. You can in theory make a DC powered motor that works without any computational power. Mostly you can see them on like very big. So for example, fans are one of the clearest examples of it. Maybe if you have like a very old fan that you just hook up to the power outlet, and it just has like a knob or one switch, and very old, and you just connect it and it works. Those are one example of an electric motor that works without pulse width modulation. That's the exact name of like the computation of selecting where a wave is gonna land. Yeah, I'm oversimplifying the things a lot, but I'm trying to explain this. So you can those kind of motors do exist, but most modern electric motors use actual pulse width modulation, because not only you can adjust the power of the motor, but they're more efficient. You can make them smaller, you can make them with different materials. Maybe you don't have a magnet, you don't want to use a magnet. Maybe you want to make them compact, and having a magnet is too big, and then issues with interference with, there's many reasons why. There's actually many kind of electric motors too. You don't need to use one type for like many different applications. You can use a different type of motor. But yeah, the type that I'm trying to learn, it's one that requires pulse width modulation. The actual type of motor that I want to build It's called an induction reluctance motor. And this, I can tell you, it has a magnet because it sticks to my steel welding table. An induction reluctance motor, there are not many, like most electric motors manufactured today are not induction reluctance motors because they're a relatively new technology, and besides, with those motors you had to have computation to make them work. The advantage of those motors is that they don't require a magnet. They just send a very large current through a conductive material to create the electric fields. But they do it in a certain way that you don't require a magnet. You pass the electric fields through the shaft into the stators outside. Usually electric motors, you only conduct your electricity either on the shaft or more commonly on the stators outside. You don't actually conduct electricity from the shaft to the stators or from the stators to the shaft. That's not really how motors are made. It's a little bit more complicated. But, the advantages with those motors is you don't need a magnet. No magnet equals cheaper. And yeah, that's pretty cool. So, just to finish the review on this one, the book is pretty nice. I guess now I can switch to my face. The book is pretty nice. I would definitely recommend it. It's very cheap. So you don't need to worry about spending a huge amount of money. Like if you buy it and as a gift, let's say, and they never use it, it's not gonna hurt you that much, man. It's just $50. And it comes with a very neat board and a couple of things that lets you do. So this is Project 10, and Project 10 worked. That's something. 9, it didn't. The fucking pin thing, it didn't work. But yeah, this more or less is gonna be the couple of next videos that I'm gonna make, because as I said, I'm not really just interested on doing this. I'm actually looking to do other stuff, but it requires pulse width modulation, and I had to buy a board that could do that. Now that I'm finished with this, I'm just gonna turn it on one more time because it's cool. So that's on, and it spins. So the power supply works, and the board works. It's cool. Oh, okay. Now, I am gonna talk about why pulse width modulation it's important. Is this thing off? Why is it not off? Oh wait, what? Oh wow. That's interesting. So the board was actually powering. Yeah, I'm not gonna talk about it. That really shouldn't have happened, but whatever. I didn't turn the thing off before I disconnected it. That's why it was weird. Now, why pulse width modulation is required and it's important to this type of stuff, and I'm gonna draw it for you. It's really just gonna take like 5 minutes. Man, where's my notebook? Okay. So the very basics of pulse width modulation is this. If you connect your I am going to show this stuff on a machine that's called an oscilloscope, and you're going to be able to see very clearly. That's why I got an oscilloscope, but you know, I haven't connected it or anything, so I cannot use it right now. But let me show you why it works. If you connect your two cables, so it's one connector, but if you see a connector, it has two cables sticking out, right? If you connect it and then see the electricity on an oscilloscope, you're gonna see this. You're gonna see one wave going like this and another wave going the opposite direction. This is what you're gonna see if you connect your outlet to a connection. Now, what this means is that you're having one connection is 60 volts. No, sorry. One connection is I'm sorry. The total voltage is 120 volts. I'm actually a little bit lost here. Oh yeah. Actually, I think this is wrong. I think you have to measure it up to here, and it's 120 volts. So this is what you get when you connect your outlet to the power supply. Now, this is two-phase because you have one wave and then the second wave on the opposite side. When your wiring on your house only uses one wave at a time, especially on the US. I don't remember in Mexico. I didn't study this in Mexico till I know for sure. But on the US right now where I'm living at, which is New York, you have two-phase, 240 volts AC power, but at any moment you only use 120 volts single phase at 60 hertz. So that means that every connector in your house, it's only using one wave at 120 volts. Now, you can wire your house and your panel supply to get 240 volts with a opposite side wave. So it's 60 hertz. It goes from 240 to 0 to 240 again, but you're getting 240 volts at the same amperage. That is how it works in the US. I know in Europe they use three-phase 240 volts or 220 volts. I don't remember exactly what it is, but there is very different ways of providing electricity. This is two-phase. Single phase would look like this, and three-phase you have three waves. I cannot actually draw it very well, but they're offset from here to here. So there's a wave going like this. If I can draw it properly, I cannot draw it properly, and then there would be one on this side. So yeah, I cannot draw it properly very clearly, but that's on Europe. Now that's AC. Some electric motors can use this one. The old ones use this power supply, and it has to be exact, okay? It has to be, well, it doesn't have to be exact, but your motor is gonna spin at an exact speed. It really depends on like the size of the shaft and if it has any gearing on it. But like if you use this type of electricity on a motor, it is gonna spin at this exact waveform, like that's what you're supplying it. Now, you can have DC power supply, which is a single line at, let's say, 36 volts. That's a very common small RC car engine, or like very small type of electric engine. In fact, I have an electric bicycle. I built that bicycle, and the front tire, it has you cannot actually see it because of this. Okay, and that front, it has an electric motor, and that motor is a DC motor with a magnet running at 48 volts. So this type of motor uses, this would be 0, this would be the origin of the graph, this would be X, this would be Y, and you can run the thing at 36 volts. Now, I showed you on the video that you could lower the voltage a little bit and make it spin slower, and you could increase the voltage and make it spin a little bit faster. Now, because of the transistors on the circuits, there is a lower and there is a higher limit to it. You cannot run, let's say it runs at 100 volts. You cannot run it at 1 volt and expect it to work at 1% of power. The same reasoning goes to every number. If you have a 100-volt engine, magnetic synchronous engine, and you provide 50 volts, it probably won't work at 50% of power. It won't supply the 50% of the torque that is rated for. That really depends on the engine. Usually how it goes is on the upper limit, the graph. So if you make a graph, right? This is the graph y, x. On the bottom, let's say I'm gonna put, on the bottom I'm gonna put, how can I draw this? The voltage, and on the top one, I'm gonna provide the torque. No, it has to be the other way. This has to be the voltage and this has to be the torque. If the motor is rated for, let's say, 48 volts, like the one on my bike, it's gonna supply no power at all at the first few volts. Then it's gonna rapidly increase and then it's gonna level off. And every increase on the voltage is not really gonna provide you much more power, because there's an upper limit to how much it can spin before it starts like slipping. They call it slipping on those type of engines. Now, this type of motor that, okay, so the reason why I did this, what is pulse width modulation? So you just learned basically that you can have an advantage of a controllable engine with a DC power supply just by lowering and upping the voltage, okay? But now, I told you just right now, this is more efficient, more simple, and it is much more manufactured than this type of engines, okay? So, how can you use the advantages of lowering and increasing voltage and current on like the most typical, simple manufactured motor, electric motor available on the market? Well, you convert this direct current into this. And that is pulse width modulation. How they do it is like this. They grab the single, so they use square waves. So like this would be no voltage at all, and this would be the highest voltage possible, right? So what they do is they make like little squares to power the thing. So I'm gonna try to draw it without going out of the camera. So let's say zoomed in, it's gonna look like this. Off, on, and then off again. So this is zoomed in. In reality, it looks much smaller. It's gonna be like a line, like that. And then what they do is they pulse these lines so that every time you get more and more current, like this. So spaced out, and then again, you have current again, and then it gets spaced out again. Now, if you see here, you have more current, and here you have less, and then more, and then less. And zoomed in, every single one of these lines is going to look like this. Now, this is limited by how much I can hand draw, right? But this is thousands times per second. That's why it's called pulse width modulation, and it is computer controlled. Really, no human is involved with this. This is not even a technology that existed way back on the day, like before the 50s and 60s. So you can make a wave like this with a single current by using this method. And you can use it. This is very important today because it's available. Like, you can use it for so many things. Like, now to finish off the video, I'm going to talk about why my motivation to study this is. I've always been an advocate for higher efficiency on simply doing stuff. I like engines, I like electronics and engineering, and I've always liked just pushing for higher efficiency, being less wasteful with what we have. Now, chemistry has a big part of it because, you know, we use so many different materials today, and being wasteful kind of sucks. But on energy is very relevant too. And pulse width modulation, you can use it for electric stoves. You can use it for better efficiency engines. You can use it for signal transmitting and processing. And it's just, it makes the use of electricity so much more complex. Yes, you need a computer, but you can use electricity for so many more things that previously you really couldn't. For example, one of the projects that I have, apart from the car, is I want to actually make a circuit, an inverter, that I don't know how to explain this. I actually forgot the name too, but induction stove. I want to make an induction stove. Now, most electric stoves today actually have a coil that gets red hot. And while maybe sometimes in theory, in some laboratory, it may be more efficient than a gas stove, really is not by that much. The same applies for electric heaters that are not heat pumps with actual liquids and gases inside, like an air conditioner. Those heaters that actually use a coil that gets red hot are not actually that much more efficient than just using a gas heater. Heat pumps that are AC and heat pumps, those are way more efficient because those actually do not generate any heat. They just transfer heat between two members, the outside and the inside, the same way an air conditioner does the opposite. An induction furnace or an induction stove, it actually works different. It doesn't actually make something red hot and then transfers the heat to your stove on the top. An induction stove works by actually making your metal hot. So you cannot use any kind of pan or kind of like cooking stuff on top of it. You have to use a metal that's conductive to magnetic fields. Um, but it's the same principle that it's used in an industrial process today to melt metal. Most furnaces that make metal, like steel beams and steel wires and stuff, just industrial processes, used actually induction heating. And the advantages of induction heating is that you're not creating a heat source and then trying to transfer that heat to the surface of the object that you're trying to work with. Induction heating actually heats up the product, like the actual piece of metal gets hot, and that's how you melt it. Why induction heating was created and was used way before today. Like I'm talking, it's something that we've been doing for like 40, 50 years, maybe even more. Why hasn't induction heating been applied to regular stoves today? Well, that's because induction furnaces on industrial processes really don't need any kind of modulation or control. They just want to melt the metal. So they select a metal piece that has to be a certain thickness and you have to feed it at a certain speed, and you know for a fact that your coils and your magnetic field, it is going to melt it. You have to control how much metal you feed into the thing. Now, you cannot do that for cooking. For cooking, you need temperature control, and also depending on how thick or thin or big your pan is, you have to have some control over how hot you want it to be. And that control really isn't available if you don't use pulse width modulation and computers for it. So that's why it took so long for the technology to get here. But it is available today. You can actually buy. Don't look just for an electric stove, because those are the ones that get red hot, not really that efficient. They consume a lot of electricity and make a lot of heat too. But you have to specifically look for a stove that it is a true induction stove. And they are going to warn you too that you have to have specific pans and, bowls and stuff like that, because it doesn't work if it's not a conductive metal. But yeah, those are available today. I think they're a little bit more expensive than regular stoves and electric stoves. But finally, we're changing to a more efficient technology after like many years of people arguing that, oh no, gas is so cheap. Why would you want to have this and that with electricity if just gas is so cheap? Well, today it isn't, man. So, it is good if you know about this stuff. It is way more efficient. It is better for the world. So you should get it. And I am trying to learn about it. I am trying to teach as many. Well, that's not true. Mostly I do this for me. I want to learn about this stuff and I want to make it. It's a lot of fun. So I think that's it. This is the very basics of pulse width modulation I just showed you. And some stuff out there requires pulse width modulation. You cannot use it if it's not a very controlled pulse of electricity. And it provides advantages, disadvantages, but it's pretty cool. Okay, so let's start with this. I am building a circuit. It's a very simple one, and this is the book that it comes from. I would actually really would recommend this one if you're like trying to learn electronic stuff, because it covers the very basics. It's really meant for like kids and teenagers. The cool thing about it though is that it has some very simple projects and it's very cheap. It's really like $50, I think it was. And you know, for $50, it is actually very cool. Like you get a lot of stuff. Um, I pretty much skipped all of the before. I read the book almost entirely, but I did skip like almost all of the first projects because you know I don't really care about those that much. Really, the reason I bought it. So maybe I should talk about that. The book, it's an Arduino Uno. Um, but this is like a so instead of just getting the board, which is really what I wanted, it's more like a kit with like a starter thing, and it gives you like a couple of things to do. It comes like with an instruction guide slash book, project book, and right now I am doing chapter 10 or project 10, which is like a small motor that you use. And where's the motor? I don't know where it is. I think I left it somewhere here though. Ah, cabrón. ¿Dónde lo dejé? Oh, it's right here. So this is the small motor that is gonna power. So as you can see, I'm like halfway there. I'm almost done. And I wanted to record it because yeah, there's not much guides and stuff like that about this kind of stuff. So since I'm learning it all on my own, I kind of want to make it a little bit easier for everyone else to learn too. So one reason why I'm trying to learn this stuff is because I'm trying to make an electric car. But you know, the electric car is not just like the whole part of it. Really, I want to learn about electronics, and one of the things that I want to learn about electronics very well is designing inverters and using AC to DC power conversion without with you know switching with transistors, and I want to build that kind of stuff. And for that, that's why I got the board, because the board actually has a little bit of capabilities of doing switching stuff. Um, but you know that's very far ahead. Right now, I'm not doing that right now. As you can see, I'm just doing the small motor. But let's continue. Right now, I'm like halfway done. So for example, here I need to connect the motor. The motor goes here. And here. Connected the power, the comms, the grounds, the power here. So I'm missing 3 comms on the top, right? The transistors. So I'm missing 3 comm wires. You could think of it maybe as a, this is not a full review of the product, but yeah, it's pretty cool. I would recommend it. It's not bad at all. Maybe it's a little bit kind of basic on the stuff that it covers. But again, for $50, I mean, realistically, you're buying the chip, right? But it comes with a pretty cool tutorial. You can think of it that way. Like it's for free. It's like a tutorial box that comes with the chip. And for $50, it's really not that bad. And by the way, I had never ever done this before. Well, this is the first time that I kind of like learned about small circuits making. Mainly I deal with like bigger stuff, but yeah, with like small stuff like this, I've never ever dealt with before, and my fucking hands are too big. I'm always fucking struggling trying to put this in. So that's the two comms, and I need the third one that goes to that one, and I connected it on this side. There is a chance that this won't work, but let's see. So this is all connected now, as is instructed on the book. Now, the second thing that I'm going to show you is that it doesn't actually connect it to a battery. No, here's it. It connects it to a battery, but I'm going to connect it to this stuff. This is an adjustable power supply, pretty much. I got it because, again, this is not the only thing that I'm doing. I'm doing some other stuff too. So it was gonna be pretty useful to just not rely on batteries or a single power supply that I have to get a specific transistors and resistors for it, because I don't want to do that. It's just better to have a little bit of variability on the power supply that I have. So I am gonna be using an actual power supply, not a battery. But I'm done. This is all connected. Now, once the thing is connected, you have to upload the code. There's a code. So I'm gonna upload the code. So how you do it is this. You grab the thing, it comes with a wire. It's a USB 2, I think it's called. And you connect it. You download the IDE, and you upload a code. Either you can write it down. I already saw the thing, and when you download the Arduino IDE to like upload code to the stuff, it already comes with prepackaged templates, and it includes all the projects that come on the book. So you don't need to write anything, you can just upload all of the stuff. So I'm gonna go do that and then come back, and I am gonna